All right, people, this is one of the more theoretical lectures, but I know you can do this, and reach out if you have any questions. So what we're going to dig into is the real formula for UG. So once again, I lied to you when I told you what the old school formula was. So let's start with that. Which of these options is the formula for UG that we have been working with so far? All right, hope you got that right. Up to now, we've said UG was mgh, and remember the units are in joules. Oh, and the height is the height of the center of a mass. That's a tricky thing sometimes. Okay, second review question. Where do you set sea level? Right, correct answer is it does not matter as long as you are consistent throughout the problem. I know we've done some problems with like multiple objects. You can set sea level to be different for each individual object, but again, as long as when you're comparing TME at A and TME at B, you make it the same, you're all set. It is arbitrary. All right, this is a review, not a review in 2022. We haven't done this yet, depending on when you're listening to this. So I'm going to spend a little bit more time with this and speed it up if you don't need as much detail. All right, so up to now, I just told you potential energy like US was 1/2 kx squared, and UG was mgh, as we just said. All right, I just told you what those were. But as in most things in physics, there's a derivation, there's some reasoning behind where those equations or formulas come from. All right, so this is really, really important, and not sure if it's on the formula sheet or not, but I'll dig into that when I add the question to the play posit. So the change in an object's potential energy is equal to negative the work done by that object. All right, and I think this is not as counterintuitive. I think you all have TME of A plus work equals TME of B. Okay, I think that makes sense. I got some energy at one point, some energy might come in or go out, and then I have a different amount of energy. That's why I teach this most of the time, because that to me is more fundamental. But this is the definition of how that stored energy is transferred into the system or out of this, or not into an object and or away from an object. All right, so we're going to dig in to make sure that this makes sense. Okay, so the work done for a force that's constant is negative FD, sorry, the negative comes from the definition. You got to be really careful with that. Okay, that is super, super important, and we'll see why. So it's negative the work, and the work is FD cosine theta. Right, so let's say we're looking at this basketball that is falling. We're going to find the change in potential energy from point A to point B. That is just some distance h. Okay, so what do? Remember, work is fundamentally has to do with forces, so draw a force diagram. The force on that basketball is mg. So the change in stored energy going from A to B is going to be negative. Remember, this is magnitude of force, magnitude of distance, the cosine of the angle between the force and the motion. Okay, and it was going down. So that cosine is 0. They're going in the same direction. So the change in stored energy is negative mgh. That is why we need that minus sign. is because the force was doing positive work. Quick review, positive, remember objects themselves can only gain kinetic energy. So the object's kinetic energy is going up from A to B. Where did that energy come from? It came from the stored energy. So if the kinetic energy is going up, the stored energy has to be going down or decreasing. So my change in stored energy is negative because the change in kinetic energy is positive. Okay, so that is why that minus sign is in there. So I'm going to take a quick, I'm going to pause this, go check out the AP formula sheet and let you know if you get that formula. All right, I have bad news. You should memorize that the change in potential energy is negative the work done by the force, not by the person. Like, so when we dropped the basketball, we were looking at the work done by gravity. If so you want to be really careful that you're like looking at the force caused by the work done by the force, not the work done by the person lifting the basketball. Okay, so this is what you get. Quick review, just since we are talking about energy. I don't love this. This is the change in energy is the work done. It seems really vague to me, because they're not saying whether it's potential or kinetic. So I don't really like that. This is a really solid definition of work that's always true, whether the force is constant or not. We're going to dig into that in a second. So what I don't like about that is it's not going to help you see that minus sign. What will help you see the minus sign that you do get is this over here, force of a spring, Hooke's law, K delta X, but there's a minus sign there. Energy, the stored energy in a spring, 1/2 K delta X squared. So looking at these two formulas, and on the formula sheet, it's about here. Like there's this whole list of definitions, and you can see this is right at the top. So this is clearly the left-hand column, and this is the right-hand column. That, if you look at those two things, and then right next to it, that means that F is minus du dx. Right there. So again, they don't give you this formula, which I think is dumb for all the other things that they give you, but these two things will give you a hint that that's the relationship. And then if you solve that for du, you get du equals negative the integral of f dx. Okay, so I think this is a super fundamental concept. Please write this down. This is the only hint that you get on the formula sheet about this relationship. So this is what we're digging into here, is that the change in stored energy is negative the integral of f dx. Hope that makes sense, because I want to move on and not spend too much time on it. Okay, so as I just said, if the force isn't constant, you cannot use FD cosine theta. You have to integrate every instantaneous force with a little bit of distance and keep track of the cosine theta. Again, this minus sign is part of the definition. It is not the negative sign from the cosine theta. All right, and for reasons that I'll talk about later, it's good to have a definite integral going on there. All right, so this is the general definition of the change in energy caused by a force. All right, so we're going to use, I wanted to make sure that you understood a little bit about where that stuff came from, because we're going to derive the real force of gravity. Now you get the real force of gravity, I'll show you in a minute, on the formula sheet, but every 8 to 10 years, 6 to 10 years, they have you either, the problem will say set up an integral but don't do the integral to show what the stored energy is, or they actually say derive the formula. All right, so I want to go through the derivation so that you can replicate it. Again, there's a small chance you will need it, but it does show up, right? So quick review, because it's been a while since I've made the module. This is the formula for the force of gravity, the real formula, which you also get. All right, so we're just taking the definition of how do you find the formula for stored energy. You have, again, the minus sign is part of the definition. You integrate the force with distance. So I need to talk a tiny bit about what dr is. So we're going to find the stored energy due to the Earth, and since the Earth is pulling, the force is always pointing towards the center of the Earth. If I move non-radially, that force is perpendicular to the motion, and cosine is 0. Right? Remember when we did, like, I'm dragging a suitcase this way, that's my motion, the normal force wasn't doing any work because it was perpendicular. Okay, so we're being lazy, clever, and attractive, and we're only integrating with respect to radial, because if I move non-radially, the Earth doesn't do any work. Right? So if I go on a roller coaster, the higher the hill, the more stored energy I have, but a hill over here that's 3 meters high is the same stored energy as a hill over here that's 3 meters high. I don't gain any energy by going this way relative to the Earth, only this way. All right, the other thing that you need to know is that by definition, dr is pointing radially outward. Okay. The minus signs are really tricky. The actual calculus is not hard, but let's go through this. So the first minus sign is the definition. I've got to integrate because it's calculus. This is the formula for the force of attraction between two objects. Constant, mass of the Earth, mass of the second object, over how far apart their centers of masses are. So this is r. Cosine of theta, we're going to dig into, well, we'll do it right now. We'll just put it above it. So dr is radially outward. Okay. The force, by definition, pulling towards the center of the planet is radially inward. Okay. So this is outward, this is inward, the force. So therefore the cosine, the angle between outward and inward is 180. Okay, so this is 180. So I got the minus sign from the definition. I can pull out everything that's constant. I have this additional -1 because the cosine of 180 is -1. So I have another -1. And then I've got dr over r squared from r initial to r final. Okay, so I've got two negatives, so that becomes a positive. These are just constants. And then I'm going to be lazy, clever, and attractive and call this r to the -2 dr from initial to final. And then this is just a polynomial where to integrate, you add 1. So that's going to make it r to the -1 divided by your power, your new power, and I'm going to evaluate that from initial to final. Okay, so again, what is super confusing is, here's another minus sign. So the minus signs just seem to appear and disappear. There's a reasoning behind all of them, but it is a little tricky. So minus sign from the definition, minus sign from cos 180, boom, those cancel, and then when you take the integral, you get the third minus sign. Okay, So, and then we're going to just evaluate our limits. We are almost done. So let me write it this way. So the change in stored energy is negative Gm1 m2 over R final minus negative Gm1 m2 over R initial. Okay, so I want you to look at this really closely. If this is the change in U, it should make sense that the general formula for U is negative, right? Because this negative is part of the final answer. This negative is from the difference, right? Final minus initial, but this minus is in both of those terms. So the real formula for the stored energy, UG, is negative G M1 M2 over R. Okay, so again, occasionally they will have you prove this, and the tricky thing is all the minus signs, but I also think this is a good review of what the definition of stored energy is. Okay, this is the final formula in nice, neat handwriting. U sub G. This is where you get it on the formula sheet. So again, the formula sheet is kind of like this other side you're going to ignore. That's for the second part of the AP, but I want you to get used to seeing it there so you don't freak out. So the formula sheet, this side is all electricity and magnetism. Don't worry about that. The left side is what you care about. Up in this corner is just defining all the variables. You should know all that. So this, what we're looking at right here, is at the very bottom. Because people tend to do it last. All right, so let's quickly go over what you get. You get the force of gravity. All right, that's the formula for the force of gravity. It's the magnitude. It is pointing toward, that's what these bars mean. It's pointing towards the center of the planet. I already made a module about that and circular motion. This is the real formula for UG. Notice the minus sign. We're going to talk about that. I got a couple more slides. So you get these two. So the only reason you need to do the proof is if they ask you. All right, where is sea level? In the previous formula for UG, MGH, H was sea level at wherever you set it to be, right? So here's your sea level, and as you move away from sea level, UG becomes more and more positive. So I'm gaining UG as H goes up. And I'm losing UG clearly as H goes down. All right. Reason I made a big point about that is here's our real function. Don't forget that minus sign. Where is this function 0? Okay, so I did a Google search. This is the inverse function. Remember, this is minus the inverse function. So this potential energy graph looks like this. We're not going to deal with negative R. So it's an inverse function. Where is this function 0? At infinity. That's kind of weird. So we're going to talk about that for a little bit. Okay, so the real formula defines sea level at infinity. This may seem arbitrary, but hopefully if you think about this, it makes sense that it is the only well-defined position to put it, because it is only when the moon and the earth are infinitely far apart that they're really not storing any energy, right? What does storing energy mean? It means here's the earth, here's the moon. If I just put these two objects at rest in the universe, they're going to accelerate towards each other. Again, we tend to think of the bigger object as winning. They both actually accelerate. It's just that the moon's would be far greater. Okay, so why do they have stored energy? Because if I put them at that location, they are going to pull on each other and give each other kinetic energy. And so the only way for them not to have that effect on each other is if I put them infinitely far apart. Any other location, I put them some distance r away from each other, and they will start to convert their potential energy to kinetic energy. Because remember, things want to find the lowest potential energy level. All right, so hopefully that makes sense. That only at infinity would they have no pull on each other, so therefore no stored energy. The other mathematical thing that makes sense is the reason I made a big deal about showing you that if you lift something up above sea level, it gains, it gets more and more stored energy. For this new formula, instead of becoming more and more positive as you move away from the Earth, it's going to get less and less negative. Okay, so you still have the same mathematical effect in terms of change. All right, I know this is long, but please bear with me. All right, so one way to visualize this function, I think Einstein did this to think about gravitational potential energy wells, that the more massive object creates this well in space that falls off as 1 over r, the inverse function. So a side view, it's like you take a sheet of rubber and you've made this dent in it. And another quick review of energy and forces, the slope of the surface is the force on the, I'm calling this planet or satellite. So this is the sun and this is the planet maybe. Yeah, call this satellite, sorry. Okay, the closer the satellite is to the planet, the steeper the slope, right? That makes sense. The closer the moon is to Earth, the greater the attraction. And the only place that that surface is truly zero and there's no force is at infinity. Even if you put the moon here where it's really, really shallow, it will speed up at an increasing rate and crash into the Earth. Okay, so that's another way to think about potential energy functions. Quick review, just to pull things together, of potential energy function graph. Remember that you mark the total mechanical energy. So this is a glider between two springs. So this is your stored energy function. You mark the TME. That's your turning point, because if this is your stored energy at some point, then this must be your kinetic energy at some point. So the pink plus the yellow add to the total. Okay, so the red graph is your stored energy, the pink line is your total energy, and what the difference is, the kinetic energy. Okay, I think this is, nope, we got a couple more, but we're in the home stretch. This is the inverse potential energy function, and I wanted to give you that super quick review so that you would remember, oh yeah, this is our total energy. Remember that I marked that on my diagram. This graph is my stored energy, and what the difference is, this green stuff is the kinetic energy. All right, so let's pretend like, so this is the sun, let's pretend like we put the Earth right here at rest. It would move towards the sun, gaining speed, right? Because the sun is doing positive work on it. It's pulling it in the direction of motion, and what's going to happen to the kinetic energy? That green or aqua thing area is increasing. But again, I'm sorry, we're not looking at the area. We are looking at this right here. This is my kinetic energy. This is my kinetic energy. So that again makes sense. You put the planet here, and at rest it will fall towards the sun, increasing in kinetic energy, and then hit the surface of the sun with this amount of kinetic energy. Okay. remember, quick review. We did this with the formula at the beginning. The force is negative the slope of this graph. So you can see that the force increases as you get closer to the sun. Okay. And the reasons the planet don't crash into the sun is because it's not placed at rest there. It is given some tangential velocity, and so yes, it has a force, but that force is centripetal. It's just what it needs to be to turn it. Okay, so there is a force there, but it's just enough to turn it. Okay, one final warning. Occasionally they will have you pick on the multiple choice, pick the graph that represents the stored energy. And so know that you're in the fourth quadrant. I think I'm going to talk about this more in the next play posit, that the stored energy should be negative. I'm sorry, the total mechanical energy should be negative, but the stored energy is definitely negative. But the function that we have defined, so the main point of this video, this new function, is only defined up to the surface. For reasons that are complicated, reach out if you want a video. They did put that on the AP once, but don't fall into the trap that this function, a regular inverse function, would be what I had earlier, where it asymptotically approaches the y-axis. This function stops at the sun. It actually is linear. I'll just tell you that now in case. So there's a linear relationship. So sorry, trying to finish this up. I know I'm at 26 minutes. This function stops at the sun, and then I will make a separate video if you want to prove that inside the sun it's a line. Whew. Okay, main point of this was quick review of what stored energy means, looking at stored energy graphs, and getting used to this new formula. All right, it was long. Thanks for your patience. See you in class.